Welcome back to our video module on dynamics. Previously, we had looked at collisions in 2D, and we looked at a point mass. One of the things we started off was some point mass coming with some initial velocity, and we wanted to know, based on, how elastic is the collision, how plastic is it, what is its final velocity. But I want to know what happens if instead of a particle, we have some sort of body going into the wall, and maybe even an irregular shaped body, and maybe even a body that has some sort of initial angular momentum. Now, what happens before and after the collision? Today, we're going to extend what we know about collisions to also include rigid body collisions, not just particles. So first, let's redraw something that we can kind of play with a little more. We're going to, as before, we're going to pretend that we have some object traveling towards a big wall. That object has some angular velocity initial, and of course, it'll have some sort of velocity initial. Now let's redraw this for convenience. This yellow spinning object is coming towards the wall, and we're interested in what's happening right before it hits the wall. So here's the wall. It's a molecule away. It's spinning, coming right towards us, and we want to know what's happening. Now I'll tell you right now that unfortunately the number of equations is just enormous for trying to solve this any normal way. If there's some sort of elastic collision or anything like that, it's hopeless, give up, walk away. All right, it's not that bad, but it is bad. So today I'd like to look at a hypothetical. What would happen if this collision was fully plastic? This'll make it a little bit more manageable for what we're doing today. So let's use conservation of angular momentum. So we know that the initial angular momentum equals the final angular momentum as long as we choose it about a point where there's no moment. Well, let's choose point A right here. Right there, there's only a force. It can't apply a torque, so we know there's no change in angular momentum. So in this case, the initial angular momentum is going to, obviously, there's going to be some due to the spinning of the object. That's I center of mass times the initial angular velocity. But then there's also going to be some, because if you'll notice, the center of mass is moving in a velocity and it's not necessarily in line with the point of contact. So you're going to have some angular momentum due to the motion of the body. This is simply the position of the center of mass with respect to A crossed with the mass times the velocity of the center of mass. And this is equal to the final angular momentum. Well, the tricky part with the final angular momentum is we don't know what the relationship is between the final angular velocity and the final velocity. We don't know what those are. So our workaround is that we look at what's happening the split second after the impact. And the split second after the impact, these things at point A, they're just still connected. We can think of this as a rotating object. We can think of this mass as a rotating object that's pivoting about this point. We can use our parallel axis theorem when we have a rotating object pivoting at about a point. So that's going to be the moment of inertia about point A times the final angular velocity, and the moment of inertia about point A is simply moment of inertia about the center of mass plus m position squared, and remember that's the position of the center of mass with respect to A, times omega f. And obviously on the left we'll have all the same things. So this is the trick that we can use where we're looking at a pivot of the body. Now we have some sort of initial condition here. Whoops, that's initial velocity. And we have a relationship between that and the final velocity, or at least the final angular velocity. Now we have the final angular velocity we can now keep our perspective of some sort of pivoting member, and we know that the velocity of the center of mass, in other words, that final velocity, if we think of this as a pivoting member about A, is going to be equal to omega crossed the position of the center of mass with respect to A. Feel free to take a moment to kind of think this one through as you look at the body pivoting about A, the split second after the rotation, if we already know this. So this is how we find the relationship between the final angular velocity and the final linear velocity. Finally, many times we want to know the impulse, find whatever happens at the wall, and that is the change in linear velocities, so that's mass times the final velocity minus the initial velocity. So in summary, when we're dealing with plastic collisions that involve rotating rigid bodies, we use the conservation of angular momentum about the impact point. The trick we can use is viewing angular momentum in two ways. The first way is the typical way that you think of it, where you know you have some sort of rotation, and then you have some sort of translation with the body moving about some point. The second way is to use the parallel axis theorem to understand the body pivoting about the impact point. Then, of course, we can step back, find the final velocity, or find whatever else we need to find. I hope this gives you an intuitive idea of how to deal with plastic rigid body collisions.